So today's lab is on waves and constructive and destructive interference. Some announcements. Quiz 6 is now available. Uh, just a reminder also that the lowest quiz is automatically dropped. So um, we have quiz 6 out, due at the normal time. There is, since this is the last lab, semester's coming to a close. If I have given out any makeup work, like a makeup uh, research paper sort of thing, if I've given you some sort of makeup work, it's going to be due by Monday. So get all of those in if you have something out like that. That's the last thing is student evaluations are now available. So you should see those on Canvas. There'll be that little pop-up at the top of the screen. So if you guys could go fill those out today, that would be great. That's pretty much all I'm going to have you do today. That's kind of like the thing I would check. I just want to make sure you guys fill those out. Other than that, let's get started into the lab. So, last chance for points. So it's the last lab worth 60 points. It's going to be pretty much the same as it always is. I'm going to go to FETS and do a sort of review session on waves. If it looks familiar, it's because this is pretty much what we've done last semester in 2A. So going here and sort of reviewing waves, you'll see this. In here, you can play around with it. I know that the Zoom call might not be sort of as smooth sort of to watch, but I'll try to put on slow motion at the bottom right here. This will also help for your measurements. You can see I could take this wrench and I can move it around, and you can see the wave starts to move down this string. You see it's going to be getting smaller and smaller. That's because I have damping on. There's a little bit right now. Specifically for this first part, what you'll need to do is let's reset. I don't need this system. Let's reset. I need to click on oscillate in the top left, and let's pause it before it keeps going. Oscillate. I need to set no end up in the top right. So what we're seeing is like a window. So imagine someone is standing out the window infinitely far away. It doesn't matter, but they're holding the other end of this string. So that's basically our way of saying, don't worry about the other end. So we're just watching the wave travel to the right out the window. Okay, so oscillate, no end, and we're going to turn damping, this little lever down at the bottom, we're going to turn that to none, all the way down like that. So let me let it play for a little bit. And also I'm going to click on slow motion so it's easier to watch. Okay, there we go. So now it's sort of in a regular pattern. If I step through it a little at a time, you can see it's moving to the right. So this wave has a speed, has a frequency, and a wavelength, and we're going to have to measure all of these quantities. Let's go to the instructions. So down at the bottom, we have the settings correct. Amplitude, frequency, speed and period and all of this. So what we're going to do is we're going to need to measure these. Down at the bottom, you can see there's a box for a ruler, some rulers, and you can use these however. There's this central sort of reference point. What you can do is measure the amplitude just by lining that up. What else? Frequency is given at the bottom. And there is sort of something else that we need to do. We need to find the wave speed. Now, this wave speed is not quite what is given up above in the sort of equations at the top. So right here at the top of the screen. So we're not necessarily using that for the wave speed. What we need to do to find the wave speed is to actually measure the distance it travels and how long it takes to go that distance. So let's go back here. So we pretty much want to measure a distance. So how far is the wave going to travel? Well, let's see, it's moving to the right. Let me step through a couple bit. So it's moving to the right. So let's find some starting point. Let's say I measure from the top of the wave right here, and I put the 0 mark right at it. I also need a timer, so let's get the timer out. And since I have it paused, I could press play on the timer and it's going to start sort of stepping through with each frame that I click. So I'll make it a lot easier to actually measure something valuable. So I can get a distance and I could get a time. So distance over time is velocity. All right, so we have a good way to do that. Pretty much this first part is all review on waves. So that was a wave traveling through a string. Let's look at then a wave maybe in water. So that's going to be this next part. For the same program, it's going to be a different sort of tab. So let's go to wave interference right here. So it's not going to be this, it's going to look like this. We're also going to use each of these different sections for the lab. For part 2, we're just looking at this first one. Starting out, we will have this faucet. So now imagine this is just a water faucet that will readily drip some water into this pool of water below. So pressing the button to turn it on, and it's a steady frequency that is set up in the top right. I could change that if I like. But you see we have this sort of top-down view of a water wave moving through this pool of water. I could pause, you do slow motion. I can also measure sort of some specific things about this water wave. So up at the top, I have a tape measure. I could bring that down. And on the left sort of edge right here, there's an X. And on the right edge right here, there's a red X. So I could take the right edge and sort of extend it out to measure sort of distances. So what I would do to measure a wavelength on this is I would take one side, one red X, and I'd put it, let's say I put it in the center of a bright region. So a bright region right here, right in the center. Okay, so to find one wavelength, I need to go to the place where it will start to repeat itself. So I need to go all the way. So this other end needs to go all the way out until it's also in the center of a bright region. So like that. So that would be one wavelength. Let's look at what we're doing here. So we're going to find the wavelength of the longest wave possible or the shortest wave possible. So how can you change those? Well, we have those controls at the top. We're also going to need to know the height of the tallest wave possible. So let's go back. So this is sort of like a top-down view. How do we get a height of the wave? We have the amplitude up at the top right. We can see the height if we click on this graph box right here. So like that. Let me get the tape measure out. All right. So this dotted line sort of represents where we're looking. And this wavy line right here, that's sort of now the side view of this pool of water. So let me step through it a little at a time. And actually, let me put on slow so we can watch it move a little bit. As the water drop splashes in, there's this sort of maximum. That's what we want. We want this one over here on the far left. We don't care about these smaller ones that are sort of fading away. So let's find where there's a maximum for this one all the way to the left. So I'd step through and I don't know, I'd say right around there. To measure this, each of these squares is 1 centimeter long. See, they're each the centimeter. So they're 1 centimeter long and 1 centimeter tall. You'd just be estimating what this is. This isn't the value we need. We need to find what it says in the instructions. So height of the tallest wave possible. All right, so just some, playing around with that. We're then going to go to interference. So we're going to go to this different tab. Okay, so once we're done with this, you see down at the bottom, it says interference. So we're going to go down here to interference. So now we have 2 faucets. So I can turn them both on and they're automatically going to go at the same time. We can see as they both start to ripple outwards, create these waves, they make this region in the middle that is kind of offset. And this is the constructive interference region. This is an actual thing we could see if you had 2 faucets that would drip water. So we have constructive interference right in the middle, right? This sort of black and blue area. But you can see there's sort of these dark, sort of fuzzy bands that extend outward and at an angle. Those regions, they're not really clearly defined. So those would be the destructive interference region. All right, let's see what we're going to be finding in here. Let me pause it. So what we're going to be finding is, for one, how can you mimic these patterns? So is there a way for you to copy pattern A, B, and C? All right. What we can do in the tools on the right, we could change the frequency. So how many waves per second? We could change the height. We could also change how far apart the faucets are. So these are all things to play around with. All right. After we do that, we're going to switch to light emitters. So let's go back to the simulation. There is, see down on the right, there is sort of a faucet in the middle, that's a speaker. We're not doing sound right now, but it's sort of neat if you check it out. The third one right here is, let's click on it. It is a sort of light emitter. You can think of these as two LED lights or two lasers. If I turn that one on, so turn them both on and press play. So what they're doing is emitting light in every direction. They also create some of these interference patterns. So, okay, they sort of radiate outwards. There's constructive and destructive interference regions. Let's pause it. What we're going to do later on is look at the sort of the screen behind it. So let's put up this screen right here. That's imagine I'm holding a wall up in front of these lights. So shining these two lights at the wall, there's this very odd interference pattern. So the bright region, that's where the constructive interference happens. The dark region, those are right in front of those blurry sections. Those are the destructive interference zones. All right. Specifically, what we're going to do is, how can you mimic this pattern by using light? So try your best to try to mimic this pattern. Next up, we're going to go to where the bottom, the new tab for the slits right here. Okay. So let's go to there. Once we finish with this, down in the bottom, let's see where it says slits. And I think we're going to go straight into looking at light. So clicking on the laser, and let's real quick, let's look at a light shining at this wall. So imagine this is a wall or a screen that has a little hole in it, a pinhole, very tiny, or a slit of some kind. So only a little bit of light can pass through. So let's turn it on, and light is all arranged in a certain way. It's all directed in one direction. But as the light hits this wall, so the light up here is going to hit the wall and bounce backwards to the left. There's this region right in the middle that is able to make it through. And that light that's able to pass through, it has to sort of fill out the remaining space. And that's why it creates this sort of rounded arc right here. Okay, and it sort of ripples outward like this. So let me play like that. And we have this sort of effect where, let me put the screen up behind it. So there's a wall behind this, and this is what it would look like on that wall. Bright region right behind where the light passes through the hole. All right, so this is where physicists, there's a big argument of, is light a particle or is light a wave? Which one is it for sure? This evidence right here shows that light moves in a straight line. It's very bright right behind where the light passes through the hole. So it seems like light might be a particle. All right, so while we're in here, you can look at one slit. Let's look at two. So we're gonna have two. this. And let's see what happens now. So shining lights, it goes through. And now we have these two holes in the wall where lights will do the same thing it would normally do. It fills out the space. But now there's this region in the middle that is constructively interfering with one another. And let me pause it. So this is some of the proof that physicists needed to say that light does in fact have wave properties. Because if you look at this, there's a bright region up at the top. There's a bright region right behind sort of this hole in the wall the light can shine through. On the bottom, it's right behind where light can shine through. But then there's this bright region right in the middle, and there's no light really directed sort of through anything right in front of that. So this is some good proof that light does have wave properties. And I know with the simulation, we're already seeing it as waves, but at the time it was, highly debated. All right, so what we can do in this, what you're doing in your simulation is, what would happen if, I change how far the slits are from one another? What if I, move them very far apart or really close together? Or if I make them larger or smaller, what would change about this pattern? Also, what if I just change the frequency of the light? What if it just means I change the color? Does changing the color do anything? This is what this part will investigate. All right. That. And then the final parts is diffraction. This is just some observation. Right, so diffraction screen. Okay, after we're done with this part, we'll go to diffraction down at the bottom. And you can kind of see the setup at the top. There is this laser over here in the top left. Let's turn the light on. So the light passes through this little screen with a tiny pinhole in it. And that's represented by this big square. And the pattern that is projected on a screen is represented by this. So what we're going to do in this part is, what if we make that pinhole larger or smaller? So the diameter right here. Or what if we, instead of a pinhole, what if it was an oval? Or what if it was a square? Or a grid of circles, pinholes? What would the pattern look like? And again, what would the pattern look like if I changed the color? So that's what this part will be asking you about. All right, and I believe that is it. There's a spot for your conclusion and your sort of feedback on these instructions. Okay, so I'm not checking anything off today. I just ask you guys do those student evaluations that pop up in Canvas. But other than that, this first part is just a wave review. Let me go over the notes now. Okay. Since there's a lot of sort of waves happening, wave interference. It's a lot of lines. I think I'm not going to draw that many diagrams for the wave interference. I feel the simulations will do a lot cleaner. I don't want to draw a lot of squiggly lines to make you guys probably more confused if you are confused already. So let's look at waves and interference patterns. Okay. So previously we've talked about light as a ray. That made things a whole lot easier. We could use geometry to find out where light's going. It made lenses very easy, but it was found out there is wave-like properties to light. So we need to review how waves behave. In general, waves have this property. I'm just going to write those equations again. So there's the period of a wave is 1 over the frequency of a wave. The inverse is true. The frequency of a wave is 1 over the period. You can think of frequency as like, well, the units are hertz, which just means, so the unit hertz, that's just 1 over a second. Seconds. So when we're talking about frequency, just think of like how many waves per second. It's just like a, like a timer or like someone counting. Okay. The other equations is velocity of a wave is equal to the frequency of a wave times its wavelength. You might think that, these equations are for a wave on a string. They're also, applicable to any type of wave. So a wave in water, a wave, a sound wave through air, or even a light wave or electromagnetic wave traveling through space. So the velocity, let me just, velocity, frequency, wavelength. Okay. Also, something to note about this equation is it might look like if I increase one of these two factors, variables, say I kept frequency constant, but then I increased the wavelength, it looks like I could make the velocity faster. That's not true. So increasing the wavelength, if that gets larger, that does not give you a larger velocity. So let me make a little side note right here. The velocity of a wave depends on the medium it travels through. So you can think of this as a constant value for a specific material. Each material has its own constant velocity that's a light wave can move through it. So if this velocity, so let's look at this equation, if this velocity is held constant for a material, it'll always be that constant. And then I increase the wavelength, that means that the frequency will be forced to decrease. All right. Then the opposite is true. If I increase the frequency and the velocity of a material is held constant, that will force the wavelength to decrease. All right, so just remember this side note right here. All right, let me do a few things with waves on a string. So we have, let's say we have a string that's attached to a wall. And I give it sort of a single pulse, a single wave that may move down the string in one direction. The wave will move all the way down until it hits the wall, and then it will reflect backwards towards me. So it's held, it's fixed at the wall at a single position. And it'll reflect off of the wall and bounce right back towards me. But it will be inverted. It will be upside down. As it travels back towards me. Okay, if I have the same thing, it's fixed, this string is fixed to a wall at a single point, and I give two waves, one right after another. There will then be two waves. Let's say they're both the same direction upwards like this. And they're both moving to the right. There'd be the briefest moment where the first wave is going to hit the wall and then bounce back. Well, you know, as it bounces back, it'll be inverted. So that first wave is going to be inverted and moving back, but that second wave is still moving to the right because it hasn't hit the wall yet. Like this. So these two waves are moving towards each other, and they are opposite to one another. Their amplitudes are opposing. So for the briefest moments, right as they pass through one another, they will destructively interfere. So I'd say this is the destructive interference. So they would momentarily cancel each other out. So if you took a picture right then, it looked like there was no waves at all. But that's not the case because the waves would continue to move even though they destructively interfere. That second wave will catch up, it'll bounce off the wall and follow along. And they will both continue on their way. Okay, this is where kind of like you guys can make this look better, or you could actually see it in action in the simulations. The drawings aren't as good as actually seeing the waves move. And the last one is, say I have a string and we don't care about where the wave, or we don't care about where it's attached. But I have one wave that is moving to the right, and I have another wave over here that's moving to the left. There would be a spot where they collide, where they overlap one another, and they would constructively interfere. So if this one on the left had an amplitude, this one on the right also had an amplitude 2, they would add their amplitudes together to create one wave for that briefest moment in the middle of an amplitude of 4. But again, this is just for the briefest moment, because the waves will continue to travel the direction they were originally headed. And then they would continue along their path through one another. Okay, I will call this constructive interference, because they're constructing, or they're building a bigger amplitude. Constructive. All right. Let's go a little bit over. Let's say we don't care about where the wave is moving to, or any waves coming back, or anything like that. Let's say this is a continuous wave that is moving to the right. How can I measure this wave? Well, we'll need a reference spot that's usually in the middle, like that. And from that reference spot, we can get the amplitude. Okay, and what else can we find out about this wave? We can measure its wavelength. So one wavelength is just a small little segment. This wave will go on forever. But I just want to figure out one small segment that doesn't repeat itself. So let's find a spot. Let me pick a arbitrary spot right here. Okay, and I'm going to measure that way. So starting right here, let's find one wavelength, which means I'm going to go along this wave until it starts to repeat again. So let's looking along this wave, it's going down and then it's moving up. Well, it's not right here because it hasn't repeated. It's never gone up this far before. So I have to go up and then over and then to right here. Okay, so then anything past that point has, this is a repetition of the same thing. Okay, from these two marks then is one wavelength. Let me draw that out like that. And let me call it lambda for one wavelength. And I picked two arbitrary spots. So what this means is, what if I did a wavelength for, like the peak? Is that the same thing? I can show you with this that it is. So I can take this one wavelength, and anywhere on this wave will be a point where it has gone through a cycle, and then right after it starts to repeat itself. So instead of right here, let's move it up to the peak. So that is also one wavelength. It goes down and then all the way up to the peak again, and then starts repeating itself. Or I can move it down to the trough down here at the bottom. That is also one wavelength. So it doesn't matter where you start measuring for the wavelength, as long as you get to the same spot, or the spot it starts to repeat itself. So let me just leave it up here at the top. Okay, and like I said before, with a frequency, just imagine there's this wall. It's not really a wall right here. It's just a your imagination. You're imagining this, and someone is counting how many waves pass through the wall in a given time. That is frequency. Waves per second. Okay, so it's just like a thing that's counting. What else? And I talked about velocity in the beginning. Yeah. Let me do one more small example. So I'm not going to do too many more diagrams. Oops, sorry. Let's say we have a light bulb. It's an old-fashioned light bulb. It's emitting light in every direction. So if I were able to sort of zoom in on the space around this light bulb, we'd see the actual electromagnetic waves coming off of this in every direction. Go like that. So it would look like this. Just a band. Oh, there we go. Coming off in every direction. And I'm not going to like continue it. I'm just going to use the right side. Like that. All right. So how do I measure wavelength for this? Well, it would be a similar problem. It is a wave, so I just need to find a spot, any spot, anywhere, that will start to repeat itself after I, start measuring. So let's say I start measuring right here, right in the center of a bright spot, or, a bright band. So I need to move along, and right when it starts to repeat itself, so right in the middle of this bright band, right there, that will be one wavelength. All right. Like always, with waves, I could take that wavelength and I can see it is true right here. Since nothing is changing about the light, it's not changing color or um, anything like that. I can take this wavelength and I see that it's equal anywhere throughout, any of these waves because it's all repeating itself. What else? Right, and so a lot of the simulations will do better than my pictures than I can draw. Let's go real quick. Just want to show this. You've seen these before in your, your book in another class somewhere. This is the electromagnetic spectrum. So these are just waves of the same type. So right in the middle, there's this little area right in the middle. And it's sort of, expanded on this picture. It's tiny if this was to scale. So this little area right in the middle is visible light. That's the electromagnetic waves floating in space, coming directly towards our face that are specific colors. So changing the wavelength, so just stretching this wave out a little bit more changes the color of the light. Or squeezing it in can make it more violet. Stretching it out makes it more red. So if I get a longer wavelength and I stretch it out even farther than red light, I'll start to get into infrared right here. So that becomes actual heat. Those are heat waves. There are, cameras for looking at heat patterns on like people and things like that. So if we get stretch the wavelength out even farther, we get to microwaves. These are, it's a type of wave, and those are what are actually used in your kitchen microwave to heat up your food. So the waves are so long, they're so large that they start to vibrate the water molecules in your food. So the the microwave emitter will shoot microwaves onto your food, start to vibrate all of the ice and water on your food. But the waves are too big to go through that mesh that's on this that screen, so you could look into the microwave. So that's how they don't come out. Microwave everything in your kitchen. If we stretch those waves even farther, we get into actual radio and then TV waves. So we're looking at things that are like a wavelength. A single wavelength is 100 meters or so long. Up to like one wavelength could be like the size of a football field, or even larger. If we get smaller, smaller than visible lights, those are the visible lights, just tiny enough for our eyes to pick up. If we get even smaller, it can start to cause damage to cells. This is ultraviolet light. So a little bit past violet is ultraviolet. So you can see in this little picture, the wavelengths are so small, it's so energetic that starts to cause damage to organic tissue. This is what causes skin cancer from the sun. If we shrink or we compress the wavelength even more, there's even more energy involved with the waves. So there is X-rays. The waves are small enough, energetic enough to go through and reflect off of your bones, of your internal organs. And gamma rays, they're so compressed that we usually only talk about those when looking at space objects, because those are, out in space. I think that is it, but this is all the same type of wave. It's just shaped differently. It's compressed a little bit more or stretched out a little bit. So changing the color of light is just dependent on the shape of the wave. All right. And I think that's all I have for today's notes. Are there any questions with this or the lab or anything? All right, let's go like this.